Welcome learners to this session on the topics aldehydes, ketones and carboxylic acids of unit 12 of class 12 chemistry book part 2. We will be discussing important aspects of chemistry of aldehydes, ketones and carboxylic acids in 4 sessions. In this session on aldehydes and ketones part 1, we will begin with writing the general structures of carbonyl compounds. Then the importance of aldehydes and ketones will be highlighted, followed by a discussion on how to write the common and IUPAC names of aldehydes and ketones. Then the orbital diagram for the structure of carbonyl group will be explained. Finally, the methods of preparation of aldehydes and ketones will be described. The learning outcomes of this session will be to write the common and IUPAC names of aldehydes and ketones from their structures and vice versa. Explain the structure of carbonyl group giving orbital diagram and describe the methods of preparation of aldehydes and ketones. Before beginning the discussion on aldehydes and ketones, it will be important to understand the general structure of these classes of compounds discussed in this unit, that is aldehydes, ketones and carboxylic acids, which contain the carbonyl group in which a double bond is present between carbon and oxygen atoms. In aldehydes, the carbonyl group is bonded to a carbon atom and a hydrogen atom, while in ketones it is bonded to 2 carbon atoms. In carboxylic acids and their derivatives, the carbonyl group is linked to hydrogen or carbon by a single bond, and then depending on the other group which is attached to the carbonyl group, the following compounds result. If this group is an OH group, then we get a carboxylic acid. If it is a halogen denoted by X, then an acyl halide results, and if the other group attached is an NH2 group, then an amide results. Further, if the group is OR dash, then the compound is an ester, and if the group is a RCOO group, then the compound is an anhydride. So, this was just a glimpse of wide variety of basic general structure of these classes of compounds. The actual number and the variety of compounds is really very large depending upon the nature of R and the functional group present along with the carbonyl group. These compounds are very widespread in nature and play an important role in various biochemical processes of life. Some common flavors having a CHO group in their molecules are vanillin from vanilla beans, salicylaldehyde from meadowsweet and cinnamaldehyde from cinnamon. And the structures of these compounds are shown here. These are used in food products and pharmaceuticals. Acetone, a ketone, is a very useful solvent. Other compounds of these classes are also useful in the preparation of adhesives, paints, resins, plastics, fabrics, etc. After knowing the general structure of carbonyl compounds and the importance of aldehydes and ketones, let us study now about their nomenclature. There are 2 systems of nomenclature of aldehydes and ketones. These are common names and the IUPAC names. The common names are also very popular for aldehydes and are derived from the corresponding carboxylic acids, where the IC of the carboxylic acid is replaced by the word aldehyde, and at the same time the Latin or the Greek term for the original source of the acid, that is aldehyde, is also given in the name. Thus, for CH3CHO, the name is acetaldehyde, which is derived from the word acetic acid. What is acetic acid? It is CH3COOH, and in Latin acetam means vinegar, and you know that acetic acid is present in vinegar. Similarly, HCHO is called formaldehyde from formic acid, HCOOH, which was first obtained from the red ants. In Latin, for mica means aunt. The position of the substituent of the carbon chain is indicated by Greek letters alpha, beta, gamma, delta, etc. The carbon atom next to CHO group is called alpha, and so on. The next is called beta, and then the chain goes on. For example, in beta bromo butyraldehyde, whose structure is shown here, you can see that at beta position bromo group is present. The common names of ketones are given by naming the two alkyl or aryl groups bonded to the carbonyl group. The location of the substituents on the carbon next to the carbonyl are assigned by using alpha alpha dash or beta beta dash positions, and so on. Acetone, which is dimethyl ketone, is very common ketone and has the structure shown here. For alkyl phenyl ketones, the name of the acyl group is prefixed to the word phenone. For example, acetophenone, propiophenone and benzophenone, whose structures are given here. The IUPAC names are written according to certain rules. Let us understand them with the help of some examples. For aldehydes, the names of the aldehyde is obtained by replacing the ending E in the name of the alkane to give the word alkanel, and for ketones, the final E in the name of the alkane is replaced by ONE to give the word alkanone. Now, for aldehydes, the longest carbon chain is numbered starting from the carbon of the aldehyde group, that is CHO, and for ketones, the numbering begins with the end nearer the carbonyl group, and the structures here show you this as an example. The substituents are written as prefixed in the alphabetical order along with the numerals indicating the position in their carbon chain. For example, some structures are shown here. When the aldehyde group is attached to a ring, then a suffix carbaldehyde is added to the name of the cycloalkane. For example, the compound given below is called cyclohexane carbaldehyde. The carbon atom of the ring attached to the aldehyde group is given the number 1. Thus, the compound shown here is named as 3-methyl cyclohexane carbaldehyde. For cyclic ketones, the carbonyl carbon is given the number 1. Thus, this compound, you can see the numbering is starting at the carbonyl carbon giving the number 1. Amongst aromatic aldehydes, the simplest aldehyde, whose structure is shown here, is called benzene carbaldehyde, as the CHO group is attached to the benzene ring here. However, the common name for it, which is benzaldehyde, is also accepted by the IUPAC system of nomenclature. Other aromatic aldehydes are named as substituted benzaldehydes. For example, the compound shown here, you can see that it is a derivative of benzaldehyde. Let us see some more examples of nomenclature of aldehydes and ketones whose structures are given here. Now, here you can see that this is now containing 2 CHO groups, and accordingly the name is given. Similarly, you can browse these more structures given as examples of this nomenclature. After having understood the nomenclature of aldehydes and ketones, let us explore the orbital structure of the carbonyl group. And you know that carbonyl group, that is C double bonded to an oxygen atom, has sp2 hybridization and it forms 3 sigma bonds. This leaves now a p orbital on the carbon atom, and similarly there is a p orbital on the oxygen atom as well. You can see this in the structure here. Now, both the p orbitals on carbon and oxygen sideways overlap and give a pi bond. The pi bond so formed has pi electron cloud, you can see in the structure both above and below the plane of the molecule, which was formed by the 3 atoms now attached to the sp2 hybridized carbon atom, and one of these atoms being a oxygen atom. Now, these three atoms which are in a plane, which are attached to the carbonyl carbon, are approximately at an angle of 120 degree. And you can also see that there are two electrons, which is a lone pair of electrons present on the oxygen atom. Oxygen is more electronegative, as you know, than carbon, and carbon oxygen double bond is polarized. How? You can see in the resonance structures given here that there is a negative charge on the oxygen and there is a positive charge on the carbon. Then the carbonyl carbon acts as an electrophilic center, that is as a Lewis acid, while the oxygen atom acts as a nucleophilic center or as a base. You will study more about this in the reactions of aldehydes and ketones. As a result, the carbonyl compounds have dipole moments and therefore they are more polar than ethers. Let us now understand the preparation of aldehydes and ketones. We will discuss the methods of preparation. The first method is oxidation of alcohols. You are already familiar from unit 1 that primary alcohols on oxidation using chromium trioxide give aldehydes, while the secondary alcohols on treatment with chromium trioxide give ketones. And you can see the structures and the reactions here. A better reagent for this oxidation of primary alcohols to aldehydes is pyridinium chlorochromate, which is also in the short form known as PCC and is a complex of chromium trioxide with pyridine and HCl. Such an oxidation reaction is also known as dehydrogenation. Why? Because it involves the loss of dihydrogen from the alcohol molecule, and we will next consider now second method of preparation, which is dehydrogenation of alcohols. This method is suitable for volatile alcohols and is of industrial application. The vapors of alcohol are passed over heavy metal catalysts such as silver or copper. The dehydrogenation takes place and the primary alcohols give aldehydes while the secondary alcohols give ketones. You can see the reactions of the examples here for the preparation of primary and secondary alcohols. From hydrocarbons also we can get aldehydes. How? There are two methods. The first one is by ozonolysis reaction of alkenes. The ozonolysis reaction of alkenes followed by the reaction with zinc dust and water gives aldehydes or ketones or a mixture of both depending upon the substitution pattern of the alkene. For example, if we start with propene, we will get after ozonolysis methanol and ethanol as the products, while if we start with 2-methyl propene, then we will get as a product one is methanol and the second product is propane 2-one, that means it is a ketone and an aldehyde both, while in the first case we got both the aldehydes. So, the product depends upon the starting alkene. The next method is by hydration of alkynes. Addition of water to ethylene in the presence of sulfuric acid and mercury sulfate gives acetaldehyde or ethanol, while all other higher alkynes give ketones in this reaction. You can see here the reactions shown. We will now explain some more methods which can be specifically used either for aldehydes or for ketones. So, we will first consider the methods for preparation of aldehydes. First method is from acyl halides or acid chlorides. Acid chlorides on hydrogenation over the catalyst palladium or barium sulfate give aldehydes. This reaction is called Rosenmund reduction and is shown here. You can see that if we start with benzoyl chloride, we will get benzaldehyde. The second method is from nitriles and esters. Nitriles on reduction with stannous chloride in the presence of hydrochloric acid yield amines, which on hydrolysis give the corresponding aldehyde. And you can see here this reaction is called Stephan reaction. Nitriles can also be selectively reduced to imines by diisobutyl ammonium hydride, which is also known as Dibal H, and then these imines can be further hydrolyzed and converted to aldehydes. You can see here the reaction. Similarly, esters can also be converted to aldehydes using Dibal H. Third method is from hydrocarbons. Aromatic aldehydes, that is benzaldehyde and its derivatives, can be prepared from aromatic hydrocarbons. The first method is by oxidation of methylbenzene. Normally, strong oxidizing agents convert toluene or its derivatives to carboxylic acids, but with suitable reagents, this oxidation can be stopped at the aldehyde stage also, as the intermediates form with them which are difficult to get further oxidized, and here we will consider two reagents for this, which are chromyl chloride, that is CrO2Cl2, and chromic oxide CrO3. We will first consider the reaction with chromyl chloride, that is CrO2Cl2. It oxidizes the methyl group of the toluene to a chromium complex, which on hydrolysis yields the corresponding aldehyde. You can see here the complex formed, and we get benzaldehyde as a product from the toluene. The second method, which involves chromium oxide, and it involves chromium oxide in the acetic anhydride, and it converts the toluene or the substituted toluene to the corresponding benzylidene diacetate, which can be further hydrolyzed to the corresponding benzaldehyde with the aqueous acid, and this reaction is known as Itard reaction. The second method is by side chain chlorination followed by hydrolysis, and it is a commercial method for the manufacture of benzaldehyde. And you can see here that side chain chlorination of toluene gives benzyl chloride first, which on hydrolysis gives the benzaldehyde, as is shown in this reaction. And the third reaction is Gattermann-Koch reaction. Here in this reaction, benzene or its derivatives on treatment with carbon monoxide and hydrogen chloride in the presence of anhydrous aluminum chloride or cuprous chloride give benzaldehyde or the substituted benzaldehyde, as is shown here in the example. And now we will consider the methods which are specifically used for the preparation of ketones. First method is from acyl chlorides. You know that treatment of acyl chlorides with dialkyl cadmium gives a ketone. And where do we get this dialkyl cadmium from? This is prepared by the reaction of cadmium chloride with the Grignard reagent, and the reaction is shown here. The first method is from nitriles. Here again nitriles on treatment with Grignard reagent followed by hydrolysis give a ketone, that is propiophenone, or the 1-phenyl propanone is shown here as a example, which has been synthesized by the reaction given. The second method is from benzene or substituted benzenes using the very common Friedel-Crafts acylation reaction. Benzene or substituted benzenes on treatment with acyl chloride in the presence of anhydrous aluminum chloride give the corresponding ketone, and you can see this in the reaction here. Let us now sum up what we have learnt in this session. We have learnt that a carbonyl group, that is C double bond O, is present in aldehydes, ketones and carboxylic acids. Further, the derivatives of carboxylic acids also contain this group. Aldehydes and ketones are widespread in plants and animals, and they play an important role in biochemical processes of life. They are also used in many food products and pharmaceuticals to add flavor. They are also useful in preparing materials like adhesives, paints, resins, perfumes, plastics, fabrics, etc. In addition to this, the common names of aldehydes and ketones were discussed and the method of writing their IUPAC names were explained. The orbital structure of carbonyl group was described, and finally we discussed different methods for the preparation of aldehydes and ketones, where we discussed both types of methods where we get either aldehyde or ketone, and then methods which were very specifically used for aldehydes and specific methods for the preparation of ketones. We hope that you have enjoyed by learning from this session. Thank you very much for being with us.